Hello, this is Jeff, and this is episode number 4 in the C11 Cong series. A couple of updates since the last episode, some bugs that I fixed, and we're going to make a couple of additional enhancements around the compilation process and supporting different compilers. And yeah, so let's just jump into it and go through what I've changed since the last episode. So someone pulled the code down and tried to compile it with GCC and was met with unhappiness by the GCC gods. And so there were a couple things there, differences between clang and GCC. One very interesting one related to how I was using static const integer values as constants. Clang was happy with that. It would accept that. GCC was not happy with that, would not accept that. There seems to be some relatively raging debate in the compiler community as to which compiler is correct. It seems like right now the consensus is that clang is bugged in that regard, and that is perhaps, interpreting the C specification a bit more liberally than GCC is. So what do we have to do to fix that? So if we take a look at like tile.h, I used to have static const int here, and I just replaced these with preprocessor directives. And it is, I think, fair to say that typically in C code, this is what you will see. No double entendre intended. So how does this work? What does pound define? This is a preprocessor directive, so you have to, the C compiler you can think of as two separate parts. One is this thing that we call the preprocessor. It runs before the actual C compiler runs. And a preprocessor, in this case, it's a textual substitution preprocessor, meaning that it sees these directives, things like pragma, things like include, things like pound define, and it has internal state that it maintains. These are symbols that are created within the preprocessor. So the way to read this is define this symbol with this content. You may ask why I'm putting the content in parentheses. You don't technically have to do that. I didn't do that here, which was actually a mistake on my part. However, it's just always been my practice to parenthesize things inside of preprocessor directives. The reason is that you don't always know the context in which your preprocessor directive is going to expand. And by putting the expression inside of parentheses, you're at least guaranteed that your expression stands on its own, right? It's evaluated within the context of the parentheses because of ordering. And then anything else around the context where your expression expanded then just gets the result, the actual intended result from your preprocessor directive. If you leave for instance, if I left the parentheses off on this one, this could actually end up being a problem, because depending on where tile size is expanded, the multiplication may not happen in the order that I intended, right? So by putting the parentheses around that, this is a prioritized prioritized expression for the parentheses. So regardless of where this gets expanded, I know that it will be tile height times tile width. That's the result that will then get included into the broader context of wherever the macro is expanded. When I say expanded, what do I mean? This is the definition of tile size. This is an expansion of tile size. So what happens is the preprocessor sees these special directives and it adds these to the symbol table. Then when it sees a symbol that it recognizes, it expands it. What does that mean? It means that it takes whatever is the value of that symbol in the symbol table and it puts it in place here, literally. So whatever characters are here minus, well, not minus, but including additional recursive expansions, right? So obviously tile size uses tile height, which gets expanded to parenthesis 8, times tile width, which gets expanded to this. So what happens when the compiler sees this is that we end up getting this. This is what the compiler actually sees after the preprocessor has run. And this is what actually gets compiled. Now the compiler is very smart, right? It's going to see the superfluous parentheses. It's going to see that it's 8 times 8. It's going to turn that into a constant. It's going to fold it into a constant value for us automatically. But that is how the preprocessor works. You can do multiple line macros. People always call these macros. They are macros of a sort, although to be honest, coming from assembly language, my opinion has always been that the C preprocessor is crap, and its macro capabilities are quite weak. The syntax is really, really bad. So while you can do some interestingly complex things with the C preprocessor, I really try to avoid it personally. And if you're going to go the preprocessor route, there are other preprocessors that you can drop in as a replacement for the C preprocessor that are much, much better than the C preprocessor itself. But this I had to make these changes to change the constants from what I was doing before to preprocessor directives or preprocessor symbols that get expanded. So then if we look inside of the C file here for tile, instead of the constant value I had before, I have the preprocessor value. And I had to do that for tile, for sprite, for tile map. Basically everywhere I was using these constants. I had to swap in the preprocessor macros. So a fairly mechanical transform. None of it really presented much challenge. It just was something that I had to do. That fixed the compilation errors with GCC. So now I have this set up to compile with GCC, and it compiles just fine. No problems. It also compiles with clang. Clang works either way. One of the things, though, that I got to thinking about was I don't really have warnings turned on here. So I'm going to open up. Actually, you know what? Let's do it this way. So another project that I work on my stream is called Ryu. And I just recently refactored the CMake configuration in Ryu to support setting warnings properly for different compilers. So I'm just going to borrow that here, and we'll talk about it. And this is one of those things. There used to be a saying in the mainframe world that at one point in time, someone wrote a JCL script. JCL stands for Job Control Language, and it's a very, if you look at JCL, you can Google it. It's a very kind of opaque, odd language that controlled IBM mainframe batch jobs. And so anyway, there was a saying that somebody once wrote a JCL, and then after that, it was, relentlessly copied. So with things like this, like CMake, where you're not probably going to be writing CMake code all that frequently, I think it's probably safe to say that you're going to be cutting and pasting these kinds of things a lot. I had some, in Ryu, I had some extra configuration for the warnings. I'm going to take those out. So it turns out that at the base level, Clang and GCC both kind of have the same default W-W all. However, after that, you get into details, specific details about what the compiler expects and supports in terms of warning levels and enabling and disabling warnings. So these blocks, the way to read this is we have in CMake, there's a macro called CMake XXX, and actually this should just be CMake C, so we're not doing C++. So C compiler ID is clang. Then we set the flags for the C compiler. We do a -w all, which should turn on all the warnings. This cache string compile flags force, this is just telling CMake what it should cache and not cache, and whether it should replace it in the cache, and so on and so forth. And then I echo out what those flags are so we can actually see them. If it's the new compiler, which would be GCC, then we set it again to -w all. Right now, again, these are both the same, but once you get into you start getting into customizing warnings and other compiler flags, they're not the same. So having them broken out here will just make things easier down the road. And then we echo out the flags for that compiler. Otherwise, we say, hey, I don't recognize this compiler. So we should probably say unknown compiler and no custom flag set. So now the CMake file runs. We get using GCC flags -w all. Okay. So, and that's exactly what we want. So now if we compile this, okay, so now we're getting some warnings. This is why I wanted to do this, because I knew I probably had to have some warnings in the code. I just didn't have the warning level turned on high enough. And typically compiler warnings, my rule of thumb is I try to eliminate all of them. Although in this case, I'm not exactly clear on what it's complaining about. Oh, I think I know what's going on. Maybe. Let's do this. Let's do a clean, run the build again, and stop it hopefully soon enough that I can. I didn't stop it quite soon enough. I'm not fast enough. All right, let's do this. We'll go into C11 here and terminal. Doesn't give me an option for scroll back. All right, let's see. What can I do this? There. Oh, stop. So I can see the wording. Ah. We'll do it the old-fashioned way. All right, what is it saying? Missing braces around initializer. Oh, yes. Okay, I think I do see the issue. But let's just double check. Let's do this. Let's do make clean, make, redirect this to a file. Oh, of course it won't. Missing braces. Right, okay. I think I know what the issue here is. So if we look at the structure here, so tile bitmap t is a struct, has an array in it. And so the compiler it's warning about this because technically what our code should have is this. That's what the compiler is expecting. Now, a really good thing here to figure out would be how can we do this with a search and replace? So one really easy way, let's try this with C11. I can do, let's search for opening left bracket. Oh, and actually let's do this so we don't accidentally grab the first one and the last one. Let's select all these. All right. Now I'll do the replace, and we'll replace it with 2 of them. Now, okay, what I should do here is get rid of the ones that I manually did. Okay. And it's actually called data is the thing that we're initializing. So let's do this. Let's select everything inside here. Do the replace, opening left bracket. We're going to replace it with opening left bracket dot data equal opening left brace. Replace all. Then we're going to search for the closing brace, and we're going to replace that with 2 closing braces. And do that. Then, if I do this in C11, it takes it a second, but it will actually reformat this for me, so I don't have to do it. And then what we end up with is, this is what the compiler is expecting. It's expecting an opening brace for the struct, for the tile bitmap, and it's expecting an array that initializes the data field on that struct. So let's just compile that. Okay, so we didn't get any warnings from that file, which is good. So let's take a look then at sprite. So sprite is probably the same, yeah, it's the same thing. So let's select everything inside here. Do the replace. We're going to replace the opening brace with an opening brace dot data equal an opening brace. And then we're going to replace the closing brace with 2 closing braces. And then I'm going to come down here and I'm just going to retype the closing bracket, and that's going to cause C11 to format it for me. And then if I compile that, no warnings there. And then I think let's take a look at palette. I think palette actually is okay. So palette is a struct, has an entries. Yeah, so the only thing that's missing here is I don't have the dot entries equal in this case. But I think that's okay. This one is structurally sound. It does what the compiler is expecting. Tile map, I believe, is okay, but let's take a look. So tile map, again, is a struct. So there's an opening and closing brace, and then the array, the data, right? So here's the opening and closing brace for this, and then this is all the data here. So actually that one might still not be right. Let's clean this, and then let's rerun the compile. No, it's okay. Yeah, because this is the structure initializer, this is the array initializer. So actually here we could say .data equal, and that should be correct. Yeah. Okay. So by turning on warnings, we got some warnings from our data initializers, and that was actually it. That was the only code that generated warnings. So that's a positive. And in our CMake list file, we now have some code to conditionally set up flags for the compiler. And we can also, anything else we have to do that's compiler specific, we can do in these blocks here. Now keep in mind that the CMake system is a preprocessor. So CMake runs, which generates certain kinds of project files, make files, Visual Studio project files, whatever. And depending on the kinds of changes that you make to the CMake configuration, you have to rerun CMake. Now, in my case, you know, C11 does that for me automatically. If I change my CMake list files, it will rerun CMake and it will regenerate all that stuff for me. But if you're doing this from the command line or from certain other IDEs, you may have to manually say, hey, rerun CMake to regenerate all my build artifacts appropriately. So, okay, that's good. And the other thing that I did was I added logging. So I thought, you know, it's going to be kind of nice to be able to log some stuff. And I had kind of vaguely remembered that SDL had logging implemented in it. SDL is really a nice little package when it comes to cross-platform game development, in the sense that it really kind of has all the basics. Now, not lots of fancy stuff, but it does have all the basics, right? So it has a simple logging system. It has, it actually has a file system abstraction layer for you. It's called RWOps. So there's several little things in SDL that are kind of bonuses, I guess you could say, that do make writing cross-platform game code that much easier. So what I did was, as I do with all this stuff, I created a module in our code called log, and then in the header file, I created a category enum. These map up to the categories that SDL provides, but I wanted to have, you know, an enum instead of pound defines. I have a log init, and all log init does is call SDL log set all priority. So again, most logging systems, if you're not familiar with them, they typically have several levels, right? So they have things like info, debug, warn, error, critical, things like that. And when you ship something into production, typically you would set your error level to be error or critical. You only want things to log out when something bad happens. When you're doing development, you might want to set it at info so you can get all your tracing information. Sometimes info is called trace. It just depends on the logging system. SDL follows what I would consider kind of like the prototypical, you know, info / message, debug, warn, error, critical, and then you have custom. SDL does have an additional layer called categories, so you can group things by audio, video, input, application, and things like that. So by telling the system that I want to log the default priority level of info, that means that anything that is logged to the info level and above will get written out to the log. If I had set this to error, then we would only see log entries come out if they were error or critical. And then from there, I created wrappers for all the different levels. So warn, debug, error, message, critical. Now, I'm only using message right now, as you can tell, but eventually we'll appropriately use at least warn and error in a couple of spots. We pass in our log category T, enum, for the category we want it to go to. We pass in a const char star for the format string. So this is like a printf type function. And then we pass in this dot dot dot. What is that? That is variadic parameters in C. So this dot dot dot, the way you get to that is there's a header file called standard arg, and the standard arg structure is called VA list, variadic argument list. There's a function called VA start, and you pass in your argument list, and you pass in the name of the variable before the variadic arguments start. So what this is doing is VA start is getting a pointer to this parameter, and it knows then that the variadic list starts after that in memory. And then this VA start will go through the parameters that are passed in, and it will build up that list, that args list. So then I call SDL log message v, which takes in our category, our priority level, our format string, and then the args array. And all the others, log critical, log error, log debug, log warn, they're all wrappers around the SDL versions of those functions. So why create a wrapper? Why do that? Well, for a couple of reasons. One, I like my naming conventions and my coding style better than theirs. So by pushing it down at least one level and putting it into my own module, I can look at code that is written the way I would prefer to see it. But the other thing is, too, I'm doing just a very, very thin abstraction here on top of SDL for most of this stuff. So if we look at like our game module, it only is exposed to, or not game controller, rather, game C. Our game module is exposed to very minimal amount of SDL, right? In fact, game run is the only thing that's really exposed to SDL significantly, and the initialization code. And even most of the initialization code I've kind of pushed to other things. So this is like this and the video portions are the most exposed parts to SDL. And the idea is, again, I don't want to go super crazy with it, but I do want to make it at least somewhat easy to switch things around if I need to, right? If I need to throw a different library in here, if I wanted to switch to OpenGL directly, or if I wanted to whatever I might want to do, by at least having my own thin interface on top of these things and not just directly weaving the library code directly into all the different use cases, I can kind of save myself potentially some headache down the road if I wanted to change things. So then if we want to look at, again, an example of the logging code being used, here's an example of logging out a message where we put it to the category app and we say, hey, the application window has been created. So if I run this, it always takes a second on my Mac for the debugger to kick in here. You can see that we have a bunch of log stuff now. Cong begin, create empty game context T, SDL init, all the things, image init, create application window, create SDL window, create the renderer, and so on and so forth. Okay, and so that's what the logging gets us, and that's going to help, right? Not only with debugging, but again, once this thing kind of gets hardened in a production environment, if you had problems with people running this out in the world, having the log in there and logging out error information, that can help you later on when you're trying to troubleshoot and debug things. The other thing that I did was I implemented keyboard support. So let's talk about that. So in game controller, oops. So I have this concept of a game controller structure, and the game controller really, it expects to have an SDL game controller pointer, and all the other information here about this is for SDL. However, I have this abstract function, I guess you could consider it, or a function that abstracts around checking a game controller button. And so I thought about this a little bit, and I thought, well, you know, if we don't have an actual game controller, like in other words, if my controller weren't connected to my machine over Bluetooth, this would be null, but that's okay. So what I would do is I could just check to see if we actually did get a legitimate controller at app startup, and if we did, I'll check for it. Otherwise, I'll check the keyboard. And so the way this works is like this. So in game.c, specifically in game init, we used to have a bunch of code here that would get the number of joysticks, would loop through those, would try to open them, would then get the game controller context and assign it. I took all that out and I moved that into game controller open. So in game controller open, the very first thing I do is I call SDL get keyboard state. Now this function's a little bit oddly named. What this is really should be called is SDL get keyboard state pointer. This returns back a pointer to an array of unsigned 8-bit integers that represent the scan code state for each scan code on the keyboard. So it's this array, and you can index into that array based on the scan code and see if that particular key has been pressed or not. We only need to call this once, and we only need to set the pointer one time. So we set the pointer based on what we get back from that function. And then to check keyboard state, all we have to do is index into this, this pointer, and we can check for a given scan code, okay? The next thing I do is I create the controller structure, and I initialize it to some safe values, right? So index is -1, all the pointers are set to null. Then I get the number of joysticks from SDL, I loop through, and I call the SDL is game controller. And if that's true, if there is actually a game controller hooked up to your computer, then I set that up. Otherwise, everything on the controller structure is empty and null, but that's okay because you're going to pass that into game controller close, and game controller close just checks to see if those pointers are not null to begin with. And because we set these things up as legitimate values to begin, we initialize the structure to a safe state. Then later on, calling game controller close should be safe, right? It won't try to free something that hasn't been allocated. And then in the game controller button code, we pass our controller structure pointer in, we pass in the button, and we check to see if we actually have a real SDL controller pointer. If we don't, then we just check the keyboard. And the way that works is I switch on the button that you're trying to check, and I map that to a particular key on the keyboard. So for a game like Donkey Kong, for this simple game, we're using the right and left arrow keys and the right control key to jump. So it's very simple. So button A, did you hit the right control key? And then left and right, if we're looking for D-pad left, did you hit the left arrow key? Are we looking for D-pad right? Did you hit the right arrow key? And this nicely abstracts that away so that our game code, which is in the state machine, right? So our game code just calls game controller button, and it doesn't know that it's not talking to an actual controller or the keyboard. That function takes care of that distinction, and then we just get back a true or false and then do the right thing based on that. So that works out really well. So now you don't have to have a controller attached to your system, and the keyboard will work just fine. Now, I would like to implement, so just bear with me here a second. going to run MAME, and I'm going to start up. That's interesting. Oh. All right. Yeah, I'm gonna have to. We'll use YouTube here for this. I changed my system configuration and okay, so I'm going to bring this over here just so we can see this. So this is what it looks like. This is the very first screen that we get. And actually this Donkey Kong played by, this is not even there. That's the person who's doing the long play here. This WW long play is obviously. So really the original arcade, you get the current score, the last score, the level that you're on, and your coin counts, and your high score table, and then the number of credits. So this is one of these states that we're going to have to support. So if we go ahead and let this play, right? This is part of the attract mode. This is like a pre-recorded playthrough of the game, and in the attract mode, the game just simulates gameplay by running the recorded stuff. This is like the title page. So this Donkey Kong, all of this is all tile map. The part that I wanted to highlight though is this thing up here at the top. So this 1-up high score level, this part up here at the top, you'll notice is it's static and it's fixed. And it shows up on every screen. And we're gonna watch through here for just a minute because it's going to become apparent why I'm focusing on this here in a second. And so this guy, he plays pretty good. There we go. We'll fast forward up to where he's going to clear this level. Okay, so now watch Donkey Kong. Do you see how he's being cut off here? Like that? And there's a reason for that. That's because the sprite engine on this platform is set to clip sprites at that Y position. So that's actually 1, 2, 3, 4 tile lines down. And that's 4 times 8, that's 32 pixels. So at 32 pixels high is when, at least on this board, is when sprites get clipped at the top part. And if you can tell, it appears that the clipping is different based on different levels because she's a sprite and the little help thing I believe is a sprite too. And on this level, Donkey Kong doesn't go up, he falls down. So obviously they've disabled the clipping up here on this level because they wanted her to be at the top here. And because Donkey Kong never goes up. So what we're going to have to do is something similar. We're going to have, at least for the Y position, a clip so that we can, when we render the sprites onto the foreground buffer, we don't, when they go outside of the clipping range, see Donkey Kong falls here on his head. And so nothing ever goes up or down outside of the range. So on this one, they obviously turned off. And on the original Donkey Kong hardware, that was either like a raster effect that they were applying selectively, or there may have actually been a control register on the hardware. You'll notice when the hammer goes to the left there, it clips. When he goes outside of the bounds, let me see if I can find that again here. Okay, so he's going to grab the hammer, and when he gets to the far left, notice that the hammer goes off the edge of the screen and it just clips it. So we'll have to do left and right clipping, and top and bottom clipping as well. Okay, so the reason I wanted to show that was because that's something that I realized we needed to implement. So in video.h, I think the easiest thing to do here would be to type def struct rect, and we'll call it rect, and a rect just has a uint16t left, uint16t top. Actually, let's make them integers, signed integers, just in case we want to do some squirrely stuff with the bounds. Int16t width. And do we want to do width or do we want to do, yeah, let's do width. Int16t height. So this is the left pixel that we're going to start clipping on. This is the top pixel we're going to stop clipping on, or start clipping on, and then this is left plus width is right, left plus height, or I'm sorry, top plus height is bottom. And then let's have a function called video clip rect, and this will take in a rect, and we'll just pass in a copy because I don't think the overhead of copying it is not that big of a deal. So rect, rect, and then let's do video or void video clip rect clear. So we have two new functions. One that we pass in a rect, and we're going to set a global clipping rect based on that, and another is a clear. So the clear, what I'm thinking we're going to have here is a static rect s clip rect. So the clear is just going to set everything to zeros. S clip rect, or actually, sorry, let's do -1 because we have signed values here. There you go. So if we clear it, we set everything to -1, and we'll check for that, right? Is the rect set? If it isn't, then we won't try to do any clipping. Otherwise, when we pass in a clipping rectangle, we'll just copy the values into our module static here. Just like that. And now, so different parts of the code can set different clipping rectangles on the screen for our sprites. Then in video FG, if I can type, update, what we're going to do right here is we're going to build a bounding rectangle based on whether or not we got a valid clipping rectangle. So so we'll create a new one here on the stack called bounds, and if s clipped rect left is greater or is not -1, then bounds left is equal to r clip rect, and we're going to do that for all these. And so, I don't know, is this the right way to do it? Now I'm debating. How about we do this? Top 0, left 0, width is screen width, height is screen height. Oh, I never changed these. That would be why. And you don't want semicolons in your preprocessor macros unless you really truly intend for them to be there, which, you know, I guess you'll know in that case is, when that's the case. Okay. So that fixes that. Okay, so when we clear it, what clearing it does is clearing it just sets it to the bounds of the screen. If you set a special rect, then it's set to the size that you wanted it set to. Got to change these constants. It's interesting. Obviously, GCC doesn't complain about the usage of those in all contexts, just certain contexts. I find that fascinating. Anyway, okay, so what that means is that s-clipped rect here is valid. It's just valid. We don't have to do anything special. And so, really, so I'm just trying to think of how I want to do this. Because obviously we have if ty plus y, because this is for tile rendering, right? Oh, and then for tiles, do we really? I don't think we have to clip tiles, do we? We just want to clip sprites. So that skips one. We don't have to worry about that. So if block y plus y is greater than s-clip rect top, or I should say, let's just say if it's less than that, or, and so this is where what is this? This is a uint 16. Okay, so let's do uint 32 t. Ty is block y plus y. So then I can replace this with ty. So now I can say if ty is greater than sClipRect top and ty, I'm sorry, I want to skip. So if it's less than this, or ty is greater than top plus height, then we're going to continue. So this clips us on y, and then we want to do something similar for x. So uint 32tx equals block x plus x. Oops. So if tx is less than the left, or tx is greater than the clip left plus the clip width, then we're going to continue. Okay, so let's just run this and make sure that our existing layout works properly. Oh, and it doesn't. Of course. No, we're not getting him at all. Okay. So let's do this. Oh, well, you know why? Okay. Because this is not initialized to anything, which is completely invalid. So what we need to do is in video init, we need to call video clip rect clear, right? Because that at least initializes the sClipRect to a valid set of values to start with. Okay, so now Mario's showing up again, and he's working. So now let's just experiment, okay? Let's move the clipping left in a bit, and let's move the top in or bottom in a bit. And so instead of calling clear here for testing, let's call video clip rect, and let's pass in 64. Let's try something like that. Oh. Okay, do it. Go like this. There he goes. Okay. So I'm going to run this. And I'm not seeing Mario because, yes, So see, he's clipping, although not clipping exactly correctly. Oh, okay, yeah. I see part of the problem. So yeah, so the continue approach isn't really going to work. So what we want to do is because we still want to change our source pointer and for X and Y. And in this case, we just want to increment our destination pointer by 4, right? Because we're clipping on the left edge or the right edge. So we still want the bulk of the logic to work here. So let's invert this. Let's say if it's greater than top and it's less than the bottom, then this block, oops, that block will run. We still increment our Y source pointer or source value. Okay, let's give that a shot. Okay, so Mario is hidden because we're clipping. Yep, there you go. Now it's like a sliding window on the left there. And that's what we want. And then on the right, there, see? Now he disappears on the right. So we've artificially changed our clipping for our sprites based on this logic. And this is going to allow us to do that effect. So up at the top, if we want Donkey Kong to kind of disappear as he climbs up that top ladder, he'll do that. And I guess, let's see, for testing purposes, how could we test that top and bottom one? So in the state machine, I'll say if game controller button D-pad up, then Mario goes up a couple pixels. If game controller button D-pad down, then Mario Y. Okay, so then when we set our video, yep, here we go. So let's set the top at 32. We'll leave the bottom where it normally is. Although the height, so it should be 236. So this should now be 224. All right, so let's give that a try. So if I move Mario away from the horizontal clip, right, he's visible. Now I've added in code. Oh, and only on the joystick though, because I didn't add the mapping for the keyboard. Here, let's do that. Okay, there we go. Now the keyboard and the joystick are synced up. So now Mario floats up, and there he goes. He clips. Perfect. Now if we go down, he clips down. And the horizontal clipping range works all the way there, works all the way over here. See, so now we have that invisible rectangle, essentially, on the screen that's preventing the sprite from rendering. Perfect. All right. So for today's show, that's kind of what I wanted to cover. And I'm pretty happy with that. So I'm going to comment out that test code. I'm going to put the regular default rectangle in place. Just make sure that works again. We'll review the code changes we made, and that'll be that. Now notice he blinks out of existence there because we don't really have a good clip. The clip is not set well for that because we're using unsigned integers. So really, technically, our top clip should be, our default on Y should probably be 16, right? Or 8. Let's make it 8. So, and then our height should be screen height minus 8. Or minus, do it that way. And the reason for that, again, is because I'm using an unsigned integer. If it goes to 0, then it immediately wraps to 65535. So the Y position, there you go. Now he clips cleanly at that top line. So sprites, by default, no sprites can go above that very top line on the screen. That does a clean clipping on them. We don't have that problem on the bottom because the number can go up to 64K in size. So, all right. So let's review our changes. So in the CMake list file, I added a section here that allows us to change flags for different compilers. So for the Clang compiler, this block will execute. For the GCC compiler, this block will execute. If it's some other compiler, Visual Studio, it's going to hit here. Eventually, I'll get this compiling in Linux and Windows as part of the series. But for now, I've just got Clang and GCC in here. And then in our game controller module, I added code to map the up key and down key to the button D-pad up, button D-pad down. In our sprite implementation file, I cleaned up the structure initialization. We were getting warnings for these, so I cleaned these up. In our state machine, I temporarily added some code that checks for D-pad up and D-pad down and moves Mario up and down on Y, so that we can do some testing with clipping, right? But eventually we're going to take that out. That's just there for testing. And then in tile, we cleaned up our structure initialization. This is correct now, and the compiler is all happy about that. In the header file, I fixed this pound define. I put parentheses around it. In tile map, I just put the .data equal just to be clear about what's being initialized. In video, we have a new static field, which is a rect_t. So this is our clipping rectangle. It applies to the entire region, the entire screen. Changed the screen width and screen height constants. And so then the loop in the sprite renderer just checks to see if our current Y position is greater than the top clip and it's less than the bottom clip. And if it is, then we go through the Y or the X cycle. And the same thing is our X clip. If it's less than the left or it's greater than the right part of the clipping rectangle, we increment our destination pointer, and then we increment our source pointer based on the offsetting, but otherwise we don't render anything outside of that clipping rectangle. In init, I have some test code that will init the clipping rectangle to something that actually demonstrates that the clipping is working. Otherwise, it just sets a default clipping rectangle that works globally on the screen for sprites. I changed the constants here to be pound defines. I forgot to do those. We added in our new video clip rec clear. So what this does is this just sets a default rectangle that's valid. So the top is 8 pixels down, the left is 0, the width is the screen width, 256 pixels, and the height is 256 minus the top. So if we'd set the top to 16, then the height would be exactly 16 from the top to the bottom. And then we have video clip rect, which you pass in a copy of a rect, and then it duplicates that into the static version. The header file, we added the rect structure. So signed integers for left, top, width, and height. And then we have our two functions, video clip rect clear and video clip rect. Eventually, when we get into actually implementing the individual states for the game, we're going to make use of this selectively to get sprites to clip the way that they should clip for that given level. And then in window, I changed all the constants to be pound defines. I forgot to do this one. And that all right. I'm going to push that up to the develop branch, and that'll do it for this episode. During the next episode, I think we will probably work on some more state machine stuff, and we'll start getting things, working more as a game. One of the things we'll have to do as a prerequisite to that is add some support functions for manipulating the tile map. So we want to be able to, like that top block up there that has the score and the level and all that, we want to do that all in code. Right now that's in data, which is fine, but we want to be able to dynamically generate that from our game state information. And that's going to involve us programmatically updating the tile map so that it shows, computed values for those fields. So we need to do that. We also have the situation where there's a couple parts of the game where the tile map changes, like when Donkey Kong jumps on the girders and the tiles change. We need to have some code that helps us do that. I think there's a couple other spots in different stages of the game where the tile map changes slightly during gameplay. So we need to make sure that we have support functions for those. And then I think we'll go through, we'll watch that YouTube video, or I'll get MAME working again here on my machine, and we'll go through and kind of map out what the exact states look like, what the tile map is, is it something we can just do entirely in code? Like that's another example. It might be helpful to build a function that just clears the tile map. So we have that top block, it's always there. But then like in the how high, that tile map is really very simple. Most of it's computed text. And then the little Donkey Kong image, the little monkey image, is we can just figure out what those tiles are, and we can have code that just stamps that, at different points in the tile map for us. So there's a bunch of stuff like that, ladders, and various other parts of that. We might want to have bits of code that will do those things for us. So we'll focus on that next, and slowly get to the point where we can get to the next group of functionality and start stringing things together to where we actually have a semblance of some kind of gameplay. So anyway, that's it for this episode. Thanks everybody. By the way, just a couple of housekeeping notes. If you want to watch my daily Twitch programming stream, that's at twitch.tv/nybbles.io. That's NYBBLESIO. I stream Monday through Saturday, 5 a.m. to 10 a.m. And right now, I'm primarily working on Ryu, the arcade construction kit, although occasionally I do have some other projects that I throw into the schedule. These C tutorials are native to YouTube. I'm not doing any of this on Twitch. If you like these videos, please click the like button. If you like my content, please subscribe, and I appreciate that very much. So thanks, have a good one, and I'll see you in the next episode.